This conference will now be recorded.
All right. Thanks for coming along to the ESIP and USGS Community for Data Integration IT&I, Information Technology and Interoperability webinar series. Today, we've got a presentation from Matt Purse from Geoscience Australia talking about discrete global grid systems. Something I've been interested to learn more about ever since I heard about them and have learned a bit over the year or two, I guess. I've been familiar with the concept, but this is going to be the first time I get a deep look into the technology and what it's all about. Thanks a lot for coming along and giving this talk, Matt.
Yep.
If you want to take 20, 30, 40 minutes, that's just fine. Leave some time for a little discussion at the end. I guess I will let you take it away. I know you've got a pretty rich slide deck here. So thanks a lot, and it's all yours.
No problem. Okay, thanks. Yeah, so what I'd like to do is to talk about discrete global grid systems, but focus a little bit more on some of the applications. I know some of you may be aware I've been harping on about these things for quite some time now, but often from the fundamental and sort of theoretical aspect, and which is good, but it raises a lot of questions in people's minds of, well, how do you actually implement these, and are there any implementations out there? And so I want to sort of add that little bit of extra flavor to this presentation today, which is why I'm bringing in the location index project, which is a project I'm attached to here at Geoscience Australia, which is all about bringing multiple types of data, multiple data sources together and integrating them across a federated multi-jurisdictional environment, which is something that DGGS and discrete global grid systems are very useful to do. There we are. Yeah, they're very useful, and it's a perfect the perfect problem space for them to operate in. But it's also one of the real challenges for conventional approaches. And so without further ado, I'll dive in a little bit. So I'll start with a condensed history of DGGS. So a lot of the fundamentals actually go back to the 1500s and some of the work that Da Vinci was doing when he was learning about maths and doing some art for another Italian mathematician, and he came across through this engagement with the golden ratio, which, funnily enough, is one of the reasons why a lot of his artwork is so great, is because he used his knowledge, his sort of found knowledge or acquired knowledge on the golden ratio to inform the proportions of his artwork, and so that led to a lot of his thinking, and it also led to, funnily enough, one of the delicious ironies of it's thought he built on this on sort of the concepts and knowledge of the golden ratio to then look at prisms and mapping prisms to a sphere, and through that he then figured out the maths and the mechanisms of maintaining proportions and creating a map that that was proportionate and built on an icosahedron mapped to the sphere, which a lot of the work that he did in doing that was the basis by which modern calculus was then taken forward by Newton and Kepler and the likes. The irony of it is that he did all this in the spherical sort of context, but given the materials at the time of, well, how do you create a map? Well, it's easier to roll up a flat sheet of paper than have a ball in your pocket. And so he also kicked off the whole mapping, cartography, and map projection branch of science, which in some regards is why we've ended up with a bit of a mess now now that we're dealing with so much data sort of around the globe. And so what I find is one of the delicious ironies of this is that the work that Da Vinci and his forerunners did in this space was the birth of both discrete global grid systems and that approach, and the flat Earth map projected approach. So I guess leveraging forward from there, we have a number of key players and key points. So there wasn't all that much done since that early foundational work that Da Vinci had done in the 1500s, right up until Buckminster Fuller and his Dimexion, where he used that thinking of Da Vinci's and then created some physical equal proportion, equal area models of the Earth. And then in the 1950s, there was a geophysicist by the name of Johnson who used again leveraged off that, used a quasi or a precursor of DGGS to build geomagnetic models. Again, using equal area sort of tessellations to bin the data. And then again, there was another bit of a break in that part until the 1980s and 90s when Peter Dutton, Michael Goodchild, Kevin Saar, and John Kimling started to did a lot of the sort of the heavy lifting from the academic side of things for the fundamentals of DGGS and defining the principles of, well, how would you build a consistent global grid system that worked. And again, they were leveraging off all of this previous work. And it really wasn't until the 1980s and 90s that we started to see the glimpses of the compute power that was required to truly leverage something like a DGGS. And it was in that period that the term discrete global grid system was actually formally coined. And then if we step forward, we sort of still had this sort of lull. In some regards, it's a little bit like the sort of the innovation sort of peaks and trough. So we had another little bit of a lull where, again, we're waiting on the advent of cloud computing and supercomputing to actually be able to employ these technologies en masse. And then sort of over the last decade or so, there's been a lot of work by some of my sort of co-collaborators, and about what's it about now, 6 years ago now, that's when I sort of got drawn into the whole discrete global grid system world. I was one of the early the pioneers, troublemakers. He kicked off the Australian Geoscience Data Cube, which is now branded the Digital Earth Australia. And very early on in that, I sort of recognised, well, the tiling regime and the grid system that that data cube infrastructure is based on was inadequate for integrating multiple data. We could make it kind of work for Landsat data, but if we wanted to do anything with other data other than just Landsat data, it was very hard. And that was sort of when I became aware of the body of literature around DGGS. And what struck me was there were a lot of people doing a lot of research, a lot of work on this, but they were all doing it very differently. And so you were seeing these global grid systems and data cube infrastructures all popping up, all using slightly different different approaches, slightly different tessellations. Some were focusing on trying to be equal area. Some didn't care about being equal area because it seemed too complicated, and some were projected, some were not. And the problem that this created was that no big data cube, or global reference grid system infrastructure was compatible with each other. And that was where I kicked off the OGC initiative to create the first international standard to govern global reference grid systems, so that we could then start to move towards a place where people could have multiple and different flavors of grid systems. And as we're a very diverse and creative bunch, and we always like to do things slightly different from everybody else. And so recognizing that, well, people are going to want to do things slightly different. So how do we? And the main premise of the work I've been leading through the OGC is, how do you do that for grid systems to enable that variety and those different sort of approaches, but to do so in a way that allows that benchmark and that foundation to be there to support direct interoperability between these systems. And that was kind of the premise that we started our journey through the OGC with, which sort of kind of brings us to today. So for those who aren't all that familiar with the DGGS technologies, this is my my DGGS on a page slide. So fundamentally, a DGGS is a hierarchical equal area tessellation, group of tessellations of the Earth. So with resolutions from near global scales right down to microns. Mathematically, you could go infinitely, but practically, there are hardware limits on computers, and there are also use case practicalities of if you're dealing with data that has an uncertainty of meters, you don't need to build or you don't need to traverse down a hierarchical grid system down to microns, for example. So there are some practicalities of how you might use these things. But how do you get an equal area tessellation of the globe? And more importantly, not just a sphere, but an ellipsoid. And so that's where the Platonic solids come in. And so for a sphere, which is also a special ellipsoid, but for a sphere, the Platonic solids, and there's a select group of Archimedes solids as well that produce an equal area tessellation on the surface of that sphere. And so if you want to extend that to an ellipsoid, then you need to do some minor adjustment for the surface distortions, but that's actually doable. I've built one myself to do that. But you need something like this to start off with. You can't start with a projected space, a completely flat Earth, and then wrap it around a ball to give you your equal area tessellation. It just doesn't work that way. And so so it's fun. This is a fundamental core of a DGGS. Is you start with a polyhedron, and then map that to the Earth model. You then, through a refinement of that initial tessellation, and I should stress too, when we talk about equal area, it's different to what a lot of people who are used to working with flattened projections think about equal area, because they always think, oh, it's got to be projected. What's your projection to make it equal area? And this is where we get back to, well, fundamentally, because we're using platonic solids, we have an equal area tessellation, but it's not a planar equal area. It's a curved equal surface area. But once we have that initial tessellation, we can then refine that into smaller and smaller levels, and that's usually by a fixed integer type of arrangement, where it's what one parent cell equals 4 child cells, which you can kind of see in the middle here. If I show the cursor, so we've got a larger triangle here, and it's split up into 4 smaller triangles, which is then split up to 4 smaller ones, and so on and so on. Over here, we've got a 1 to 9 refinement ratio, which goes from sort of 9 child cells to every parent cell. And there's quite a variety of these that have been shown to work, including some odd ones, which is like 1 to 7, which Uber are using in their DGGS implementation, which when you first look at it, you think that can't work, and then until you actually go step through it, and you, oh yeah, it does work. But the fundamental of this is that it's a fixed hierarchy and a fixed sort of way of traversing down through the levels. Now, another key aspect of discrete global grid systems is that every single one of these cells has an identifier, and it's identified at its centroid, and that allows we approach that from the standard perspective anyway. Of, well, we know rasters and often like images and pixels are referenced in their top left-hand corner. But when you've got a hexagonal cell, well, that the orientation of that cell is allowed to vary. Which one's the top left corner? Whereas, and the same thing for a triangular style of cell structure. But if we say, well, let's fix it on the centroid, the very middle of that cell. Each one of those cells has a centroid, which can be arrived at by exactly the same method, and that's that's from the standard perspective. That's why we chose that. But each cell is referenced, and it has a globally unique identifier, regardless of what resolution you're at, and regardless of wherever you are in the world. And what that allows you to do, and I should point, you can see there the little squiggly line there, is whilst the standard doesn't enforce the use of space filling curves or specific space filling curves, the standard itself just requires you to have a unique identifier. But most implementations, and in most cases, the best way to arrive with that, whilst making sure that you traverse the entire space, is by the use of space filling curves. But what this allows you to do, it allows you to move complex multi-dimensional spatial analyses into a set of one-dimensional array processes, and that is very powerful in terms of increasing computational speed, and increasing the ability to store data that's locally nearby each other, and actually physically store them on store information on disk in that same way. So like I said before, there's a DGGS is not a global grid. It is a system of global grids which are connected by a fixed cell hierarchy. And that is a fundamental element of it. And that allows you also to store data at multiple levels. You can have multiple levels for the same data set. You can have different data all stored at different levels, but fundamentally, the DGGS allows you to combine and integrate all of those data sort of in a consistent and sort of standardized way. And I'll show some examples of how we've been doing this in Australia later on. Now, because we're dealing with the DGGS, we create equal units, sort of, and equal partitions of the Earth. We're able to massively scale operations on these, because with each cell being an identical coverage of the surface of the Earth, we're able to throw analytical processes to cloud and HPC resources in a massively parallel way, and that again provides, in addition to being able to do these things by a set of one-dimensional array processes, which computers really love, it also allows us to do that in parallel, which is again adds to the efficiencies. And this is partly why it's taken us sort of 4 centuries to get to this point of being able to actually realize what DGGS infrastructures. So that's the structure of DGGS and kind of how they work there. But fundamentally, one of the big challenges we have when we're dealing with integrating data sets is the raster and vector divide. And this comes back to the delicious sort of irony or of the work that Da Vinci did, and is that we have the raster vector divide from when we put maps into computers. So we were very used to drawing our own maps and shading in and coloring sort of areas of those maps to represent different things. And then computers came along and we went, oh, fantastic. Well, we can take this map that's on our table and we can put that on this screen. And then we've got our map on our screen. And then, oh, well, our screen's divided up into even bits. So, oh, well, we can represent our coverages, our patches that we want to color in. We can color them in on the computer screen. But then when we want to draw wiggly lines, well, it's more efficient for us because we want to save space and save compute power, because that was a vital thing back in the 50s. Well, we don't want to have to draw every single pixel. We just want to say, well, I want to draw a line from this dot to this dot on the screen. And so that led to the vector raster or raster vector divide. So fundamentally, it's, well, what is a vector? Well, I mean, if you look sort of from a physics perspective, what's called a vector data set and a raster data set, well, a vector is not a real vector from a physics perspective, but we won't get too much into that semantics. It's an accepted term. But if we look at a road, say, from a helicopter, it looks like a line, this tiny little sinuousy sort of thing, which is what we think of as a vector object. But if we're standing on that road, is it a line? Is it a wiggly sort of thin line that's sort of got these points that have perfect precision to them? Well, no. When we're standing on the road, it's a coverage. It's got lateral space to it. And so if you're going to define what a road is, the resolution or the scale that you're defining that road has an impact as to whether you need to define it as a raster or a vector. And therein lies part of the problem of integrating multiple data sets and multiple resolutions, is that some of these things are rasters and then they're vectors. How do we do that? And one of the and this is where discrete global grid systems really do come into the fore. They really do help to this. And there's a bit of an explanation as why this. So on the left-hand side here, we've got a vector data set, and we've got a bunch of polygons there, and we've got a polyline feature there, as representing a road here and a lake here in Canberra. And one of the neat things that people have discovered and sort of engineered in vector data sets is the ability to not just record I'm drawing a feature that connects point A to point B, but we're able to store many extra parameters or attributes to that data, this sort of rich set of features. And so we can provide identifiers, arbitrary identifiers that mean something to us, but to the data it doesn't really mean much. We can provide names of this is Lake Burley Griffin, or this is Parks Way. And we can define the type of thing it is, like this is a road or this is a lake, and there's any number of features that you could add to a vector data set very easily. But the problem you've got with vectors, and I'm sure this isn't a surprise to anyone on the call, is that when you're dealing with lots and lots of vector data and you're wanting to do analytics on vectors, you've got to do lots and lots of spatial computations. Where is this point in relation to this line? Is this point inside this polygon? Is this polygon crossing this polygon? Does this line intersect a polygon? You're having to do lots and lots of in many cases, complex mathematical operations. And as you try to scale that up, you start to hit bottlenecks of what the computer can do. And this is where rasters really do come into their fore, is that if you represent those vector features as rasters, you then get the array processing capability that computers are really good at doing. And so you can start to massively speed up some of those processes. But there's a catch with the raster world, is that raster objects and raster data structures have a much more limited capacity to store features and attribute information. Often you have a single value that can be stored in a pixel at any level. You might have multi-level or multi-banded raster, but each band is a raster in itself, and each band can only store one bit of information associated with each pixel or each cell. And so instantly there you're cutting down on the rich contextual and semantic information that you can attach to that data inside that data structure. And another bit, which is probably the sort of more important and more alarming, is that if you don't get, and it's more important of when you're dealing with polylines, is if you don't get that rasterization process right, and the scale and the resolution that you've decided to rasterize your vector, then you break it up. And so you go from this nice continuous sort of feature here on the left to this blocky sort of separated and disaggregated connection. Now, to the human eye, our eyes, we can work out fuzzy scenarios and fuzzy logic, and so our eyes can see that, and our brains interpret, it's a bit blocky and it's a bit disjointed, but I can kind of see that, yeah, there's a trend there, and that's a road. But for a computer, that's actually really hard, especially when you're wanting to do comparisons. And this sort of comes back to some of the limitations that Digital Earth Australia struggles with is that for when you're trying to do pixel to pixel comparisons, it's very hard for a computer to do this at scale in this scenario here, because it doesn't know that every part, that all of the gaps in between those red blobs are actually road as well. And this is where DGGS sort of comes into the fore, because DGGS is not a single resolution image or a single resolution grid. It's an infrastructure. It's a hierarchical set of tessellations, which means that you can drill down through your tessellations to a finer and finer degree, and where needed, you can re-represent that vector object of the road at a really fine level, if you need to, that is continuous and that's connected. What's more is, because the DGGS is referenced, is a set of cells that are referenced by a unique identifier. It's kind of a bit like regular databases, where each cell is like a bucket, or you could even conceive it in your head as being just like a relational database table. And in a relational database table, you can store any number of contextual and sort of information. You can store rasters inside a database table. You can store many different additional pieces of data and information. And in a relational database, you've got a key that allows you to join your different tables together. In a DGGS, you have a key. You have the cell identifier, which allows you to link and join and work out where are my parents and where are my siblings and where are my children. And so you're able to drill down through all of this and link all of this information together. And so DGGS as a technology enable you to bring the raster and the vector world together, but in a consistent and spatially consistent way that that can be applied anywhere in the globe. So when it comes to storing data in a DGGS, we kind of have two modes of operation of how to do this. One is tightly coupled, where we're physically storing information inside the cell. So we're constructing data objects that are representing those cells, where we can store each individual observation inside a cell. All right. We can also aggregate and group multiple observations, so a group of observations, and store them all inside a single cell. But that's and that's quite useful, and there's been a number of demonstrations of where that's worked really well, and that allows you to then easily just take those little snippets and chunks of data and do work on them. I should and then there's loosely coupled, which is a little bit more of a flexible approach, where you're saying, what are the key pieces of information that I want to reference to a DGGS? So you could use the DGGS cells as coordinates, and much like the way that we represent vector objects now, where we can say, oh, here are the nodes of my line. Well, I'll reference each of those nodes to a DGGS cell, and I'll store the extra contextual information that this is point A and it's connected to point B by this type of curve, and then it's connected to point C by this type of curve, and so on and so forth. And then you can get this this view that you can sort of see here on the left. You can also use the concept of tagging, which I think is really neat, and I kind of like this the most out of all of those. Is where you can take your object and you can say, well, I want to keep my object the same. I don't want to mess with my data structures, but I want to add to it. I want to know which DGGS cells live inside or are associated with this thing. And so you can see there where the focus now has moved from being the focus on the cells to the focus on the object, and the object is then storing a list or a set of DGGS cells that are contained within it. And that allows you to still use the DGGS querying and the capabilities in the same way, but allows you to do so without having to slice and dice and change your data. Early on, one of the biggest oppositions to the DGGS approach that I found from a lot of people was the thinking that, well, we've done a lot of work to get our data calibrated and nice and organized in the way we've got it. We don't want to have to go and unpick all of that just to put it into a DGGS. And this is where the concept of loosely coupling allows you to say, well, that's fine. You can keep your data the way you want. And you can still reference it to a DGGS, but as a reference. So you either add the DGGS references to your data, or you create a separate lookup table that links the two infrastructures together, but allows that extra flexibility, which is a really important aspect. Now, when we start to do this, we start to realize that we're able to now start to integrate data, and it doesn't matter whether that data is a piece of geophysics, is some cadastre information, is some data that's come out of a data cube, or is some socio-economic or statistical information. Because using a DGGS engine, we're able to combine and bring these disparate and often siloed data sets together. And when we do this, we end up with a set of spatially enabled or DGGS enabled data. Now, like I said before, there's a couple of ways you could do this, and some people might want to tightly couple their data, and that's fine, right? What they end up at the end of it is they have a data set or a data store that is DGGS enabled. But regardless of the way that that you go about it, they're all referenced to a DGGS, and you're then able to query that DGGS engine for give me all of the data sets that are located here. And so you might set up your footprint for where is here, and then you might ask which DGGS cells are here. And then once you have those DGGS cells, the identifiers of those cells, then you can very simply do a conventional database lookup of your enabled data, spatially enabled data, and find, give me all of the data that matches these cell identifiers. And that allows you to then very rapidly and move into the space of producing integrated information. We're moving from data into information, and it's integrated. We're able to bring Raster data together. We're able to bring social information together. We're able to add real-time and time series data as well, which is really powerful. And so why standardize DGGS in the first place? Well, I did cover that a little bit, but just to underscore the benefits of that is a little lesson from globalization. So back in the 20 years or so ago, or it might be 30 years now, bilateral free trade agreements boosted trade by over 45% in 20 years. When countries all sort of kind of get together and sort of form the general agreement on tariffs and trade, sort of that produced an even greater boost, which is good. That was sort of collaborating and these free trade agreements enabled and these policy decisions. But we still had a problem, is that things were being shipped in a very ad hoc way until the advent of containerization. And when containers were brought onto the scene, there was instantly 320% increase in bilateral trade because they were able to get their goods moved in a much more efficient way. And over 5 years, over 5 years, and then over that same 20-year period, it was nearly 800% increase in trade. So by moving into a more standardized, containerized sort of fashion of moving goods, we're able to drive a massive increase in trade and the global economy. And the reason this is because the containers that on a ship, the containers fit seamlessly together. They allow for different sizes that are consistently scaled so that they fit together at multiple scales. They saves time and avoid losses of due to incoherent packaging. So everything's all there nicely sort of organized and referenced. It's addressable and traceable. Each container has an address. It can be traced wherever it goes in the sort of moves in the world. Same deal from the data landscape for a DGGS cell. And we're not having to deal with things that are just slightly a little bit different, kind of the same, but a little bit different. So they all fit nicely. And if you look at a stack of containers on a ship or in a dockyard, what does it remind you of? It looks like a grid. Looks like a grid system. It looks like a DGGS. Now, DGGS are disruptive. It takes a different approach. So if we have a little look at the way we've identified location over time. So lats and longs, they were developed for analog navigation when we were navigating around the oceans, really, and how to do that. And that's very, very powerful. But it was for analog navigation. When we're starting to do digital stuff, you kind of have some of these throwbacks. Plus, when you're dealing with latitudes, the distance between positions on the globe vary. Their relative difference versus the absolute difference varies significantly, depending on where you are in the world, which creates difficulties. When we look at over the last 20, 30 years now of the geospatial and the computerized geospatial world, I think a lot of the standards that underpin those, they're based on planar geometries because we've computerized our concept of a map, which has been planar. Even coverages and some of the more modern sort of standards and approaches are still underpinned by the flat Earth geometries of produced by projections. And like I said before, coordinates sit uncomfortably with modern linked data systems because you've got to do work on them to actually work out, well, where are they? How far is this point away from that point? DGGS cuts through all of that because it is fundamentally predicated on curve geometries, which has created a challenge, and it's a disruptive challenge for a lot of the infrastructures that are built on these standards. Like I said before, vectors, rasters, point clouds, and all that are built, fundamentally they're built on different data models and processing algorithms. Whereas a DGGS is kind of a centralized thing that is held, that enables these things to come together in a much more seamless way. And conventionally, I mean, there's no common data model yet defined for spatiotemporal precision and uncertainty. Everyone does it slightly different or has their own approach. now, and it's likewise with data provenance. So, and often that gets sort of packaged or disconnected from different data. Now, just focusing on those last two, well, with the DGGS, because you can refine your cell size at multiple levels, you're able to use the area of that cell as a proxy for uncertainty. So you're able to instantly start to encode uncertainty into your data structure without having to do it in an arbitrary fashion. You're also, because you're able to stick any amount of information, any type of information, or associate it with a cell, you're able to store rich metadata information and provenance information alongside with your data and spatially tied to your data through the DGGS. And so again, your DGGS are able to sort of cut through some of the conventional sort of approaches and thinking around this to bring things together and unify them. So we're bridging the gap between spatial and non-spatial data. So I've talked about that again, but when we start looking at statistical data, we're starting to look at vastly different. We're not trying to bring different spatial data types or data structures together. We're trying to bring completely different data. Often it's spreadsheet data that's contextual, semantic, and trying to combine that with spatial data, which is not an easy challenge. But if we're able to do that, we start to unlock and bridge some of the open up the opportunities of promoting investment and capacity building, capability building, leveraging big data and small data together to drive greater collaboration between geospatial and statistical communities, and also to identify and solve some of these really vexing challenges that climate change and other factors throw at us. With DGGS, we're able to link national, subnational, all the way up to global information to enable better and scalable decision making. We're able to, because again, it's a consistent framework that allows you to break down a lot of these silos. DGGS represent a good way to support the sustainable development goals, and also they're being actively looked at now in the context of the global statistical geospatial framework. Again, because they're an integrator as an infrastructure, they allow you to bring the social, the economic, and the environmental data all together. And this brings us to LOC-I, the location index project. So everything happens in a place, and the problem we have in the Australian environment is that everything's all disjointed. All these different agencies are all operating in their own little space. And the concept of the LOC-I project is to be the jigsaw piece that brings everything all together and to be that enabler. And the idea is to make it, is to build a system to support decisions that are fit for purpose, using authoritative sources, using world's best technologies, and to be available on demand to users from wherever they are across whichever jurisdiction they're in. So we've got a little blurb on that. So it's about a 3-minute slide if this works. Yes, which will give you a bit of context.
Everything happens somewhere. That makes information about location one of the key ways to link big data sets together. The problem has been that different agencies record location in different ways. Some use map coordinates, others use street addresses or administrative boundaries. Still others use gridded data for things like vegetation or native habitat, natural landforms, and features like river catchments. This practice of identifying the same place in multiple ways impacts efficiency and reliability of analysis. Questions get asked about people, business, and the environment every day, and the information that provides answers for the decisions government makes needs to be findable, accessible, interoperable, and reusable. Good data is essential if government is to formulate effective policies, services and programs. But without a standardised way of accessing and relating location data with others such as population, industry or climate, government often ends up with errors in any integration where location would be a key component to any meaningful analysis. And without a way to share the data, analyses remain within the department walls, and despite their great value, use the same source data for a separate project, he or she would have to replicate the process entirely. The location index, or LOC-I, will solve this problem. LOC-I will overcome this difficulty by automating the process and will introduce a level of uniformity to location datasets that will enable researchers to effectively and seamlessly integrate location data to produce accurate and repeatable results about people, business, and the environment. LOC-I will also remove barriers to sharing through an agreed and consistent way to translate and connect different methods of referencing location across government data and, subject to strict privacy laws, make it available to the wider research community. So how will LOC-I be applied? By helping the numerous agencies from Australian government, state government and local communities use LOC-I infrastructure to make informed, accurate and data-driven decisions about how to mitigate the risks posed by severe weather events and climate change, groundwater quality and growing tourism numbers, how to effectively and efficiently mitigate biosecurity risks, and how best to mobilise a response to incursions, how to generate economic growth without depleting natural resources or reducing the value, condition or multiple use of available land. Location Index is part of the Data Integration Partnership for Australia, or DIPA, a multi-agency program that will open up new ways of integrating and analysing data from different domains in a consistent and reliable way by reducing costs in accessing the data, enabling fast and easy access to the data, enabling stable and repeatable access to the data, and reducing complexity in the use of the data. It will increase interoperability with other data sets and improve decision-making through the use of trusted data. It will also provide transparency in how the data set was made and what is planned for its future. But the real measure of LOC-I's success will be the increased number of location-based data sets indexed and linked to support repeatable data integration in the future. As the community of subject matter experts accessing LOC-I grows, so too will the reference library of common analyses and outcomes.
Alrighty. So just getting interested. Sorry.
I wonder if we could. So we're out of time, and I want to keep these. I want to keep these to an hour, but I wonder if we could set up a time to do a session specifically on LOC-I, because there's probably a lot there, more than even beyond DGGS, that would be of interest.
Yes. So no, more than happy. So yeah. So what I sort of had there, and yeah, people can go through that slides, and I can sort of go through them at a later date as well. Is starting to get into more of the applications of what I've discussed thus far of DGGS, and actually showing, well, DGGS are actually a thing. And they're no longer a concept or an academic article. So yeah, so more than happy. And are there any questions on the, I guess, the fundamentals of DGGS?
So look, before we jump to questions, and I do want to open up the floor and take some time if there are questions, but just to kind of close out, next month, we are planning on hearing from Michael Riley and others from NASA who have a DGGS-like implementation in the works. That should be an interesting kind of next step in this series, in this conversation. And then maybe after that, I guess it would be great to hear about the DGGS applications in LOC-I. I think there's potentially some other things in LOC-I that we want to hear about in the linked data sphere as well. So So anyways, I think this has been a fantastic introduction to the DGGS, and I look forward to continuing to hear more and kind of talking about this, because I think it's a perfect kind of next piece of the conversation in the IT&I series. So thank you very much, and we'll go ahead and open up for questions if there are any about the basics of DGGS.
This is Mike Riley. I have one quick question comes to my mind, and want to thank you for the excellent presentation that you just put together here. You mentioned equal area. What does that mean? Because some of the things that with the stair indexing, we're not equal area. We do have a recursive tessellation of, but for efficiency and performance issues, we haven't gone to great lengths to at every level the different elements are equal area. So I'm just wondering, what does equal area mean in the DGGS context?
Well, yes. So yeah, that is I guess a contentious topic when it comes to, I guess, some of the purists versus the pragmatists. But the fundamental principle behind that is, if you have your data organized spatially or spatially binned by equal area units, then when you're doing your analysis, you no longer have to normalize your areal difference. A perfect example of this is the Digital Earth Australia. So the tiling regime that it uses is just a straight lat long 1 degree by 1 degree tile that data is then partitioned into. The problem with that is, for a country like Australia, or a continent like Australia, from the bottom of Tasmania to the top of Cape York in the top of Queensland, the size of those cells varies by over 30%. And so when you're doing analysis of data, then you have to reconcile and correctly reconcile the areal difference of the data stored that sort of in those buckets, in those bins. And so if you don't have an equal area sort of infrastructure that you're basing on, when you're doing your analysis, you have to do that work, and then sort of hope that you've done your area normalization correctly. Otherwise, you're adding, in some cases, significant errors to your data just in your analysis. So if it's already equal area, then it's less work that you have to do when you're doing your repeated analysis. So that's the principle behind equal area. Is you've got to do it at one point, right? You're either doing it when you're analyzing the data, or you're doing it when you're ingesting the data, and you're doing it once. That's the concept. But how equal is equal area? And really that comes down to your level of precision and how sort of rigorous you want to be. And this is why in the standard, and we recognize this, well, it's like, well, how long is a meter? Well, depending on how you measure that meter, you can get different measures of that meter, and with different levels of uncertainty or levels of precision of that meter. And so in the standard, what we've required is that people sort of wanting to submit their DGGS implementation for compliance need to specify that level of precision. And if you specify that level of precision, well, you are actually saying that these cells are equal area to within this level of uncertainty. And that's giving you a measure of, well, how equal area is this? And if you're putting up your DGGS infrastructure for somebody else to take off the shelf and use, you're then providing them with some metrics as to, well, do I want DGGS A or DGGS B? And for their use case, some use cases, DGGS A might be the better fit, or DGGS B might be the better fit, and one might be tying cells down to an equal area, down to the nearest cubic or nearest square millimeter, and one might be just refining it to the nearest 5 meters. Depending on your use case, one might be better than the other. But both, because they're defining their uncertainty of how equal area they are, then they still are compliant with the standard. Because same, like you said, the same topologies are still in operation. You're tessellating the Earth, you're addressing the cells, and then once you've done that and it's assigned your data, you're working in a database type context where you're using those indexes. So that method of operation doesn't change. It's just it comes down to your analysis and how rigorous you need to be for your use case. Does that answer your question?
Very well, nicely done. Thank you.
Yep.
Hi, this is Ethan Davis. Thanks for the presentation. Really interesting and useful to understand. Quick question: has there been any work done with DGGS for 3 or more dimensions? I'm particularly interested in the space filling curve aspect of the IDs. Seems really useful.
Yes. So there has been some academic work done, particularly in China. There's been quite a bit of work done. But to my knowledge, most of those are still sort of academic research sort of infrastructures. I've been playing around on the side myself, building these things, and it is possible to build 3-dimensional space filling curves. To do so, in the context of a DGGS, there's a couple of ways you can approach it. But yes, it is possible to do it. Not many people have yet sort of brought to the table a fully functioning implementation as yet. I'm hoping that sometime soon that'll happen. But because that's kind of the next step for a lot of industries. So geological and geophysical applications, 3D is what's required, or volumetric is what's required, and we're moving ahead on sort of in the OGC to support that by extending the standard specifications to also include a specification for volumetric, and then there's a few extra questions, but then spatiotemporal 4D, but at least going to 3 spatial dimensions, so that we've got so when people are building these things, they've actually got a standard that they can actually pin their infrastructure on, and also be comfortable and assured that what they're building as a volumetric DGGS will still be able to operate and integrate with surface DGGS implementations as well.
Great, thank you. Oh, also, will your slides be available somewhere?
Yes, I've shared them with David by Google Drive. Yeah, so I'm more than happy, and I'm more than happy to send them. They're about 35.
I'll attach them.
A bit hard to email them, but
I'll attach them to the ESA wiki page for the presentation.
Great, thanks.
right.
All right. Well, thank you very much. And I guess I look forward to continuing this series or this kind of theme. There's a lot more here to dig into and understand and play around with. So, yeah, thanks for taking the time. Really nice intro presentation. And yeah, look forward to hearing more in the future.
No worries. Thanks a lot.
All right. Thanks, everybody. We'll talk to you later.
Thank you.
Very good, thanks. Have a good day.